I'd like to take some time to talk to you about covariance and correlation as it applies to the multivariate normal distribution. By this time, we should be familiar with the normal distribution. Here, I've plotted some density functions. So these give us an idea of how likely it is that we will see the x values as laid out on the horizontal axis. And if we look at the blue line, I can see it would be very likely to get values around 0 and much less likely to get values near -2 or even -1.5. Now up here I have the formula for that density function, and it has a pi in there and an e. It really only relies on two parameters though, which are the variance, sigma squared, and the mean, mu. And so this is the formula that gives us these density functions which describe the distribution. Of course, the data would look more like this. These are points drawn from a normal distribution. A normal distribution as notated here with mean 0 and variance of 1. One of the reasons I like to show this picture is because it lines up with the previous pictures, because you can see I'm much more likely to get values around 0. But I also want you to consider what variance means geometrically, right? Variance is the sum of squared distances from each point to the mean. In the normal distribution, the mean is at the center. Now, this is divided by a constant, n-1. As a mathematician, we tend to just ignore that because it's a constant, but it is there. And so when we look at data plotted along a number line, the variance is the sum of squared deviations from each point to the center. That's something to keep in mind when we get into the fall lectures. Now, we don't usually have just one variable, right? So we have to introduce the notion of covariance. And covariance is a number that describes how two variables change together. So if x increases or decreases, does y tend to increase or decrease? Covariance can be negative. And it would be negative if these two variables had an inverse relationship. As one increases, the other decreases. Of course, you recall that variance cannot be negative, but covariance can be negative. And so covariance is a parameter of the joint distribution of x and y. A joint distribution describes how likely we are to see the pair x, y together. This is a picture of a joint distribution of two variables, x and y. So I can see that the likely values, right, this is the density, so it tells me how likely it is that I would see each pair of values. And it looks like it would be very likely for me to see both x and y in the range of 40 to 60, and rather unlikely to see anything beyond that range. So let me ask you this. Is it rare for someone to be 6 feet tall? Well, no, I'm sure there are several people in this class that are 6 feet tall. Is it rare for someone to be 110 pounds? Not really. There are plenty of 110-pound people throughout the world. Now, is it rare for someone to be 6 feet tall and 110 pounds? You'd probably say yes. That is a very low weight for someone who is 6 feet tall. And so that's a question that we have to look to the joint distribution of height and weight in order to be able to answer. So let's explore this a little bit further. Let's suppose that x and y are normally distributed. Y will have mean 0 and variance of 2. X will have mean 0 and variance of 1. So here I have plotted the density function for y. You can see it's a little wider because it's got a larger variance. And the density function of x. And this would correspond to a two-dimensional scatter plot of data. So here I have x and y plotted on a plane. And what I want to realize is that these two pictures here are not enough. These two densities would help me, again, answer the question, is it unusual for someone to be 6 feet or 110 pounds? Both of those values may be well within this distribution, but when I combine them, I fall in an area there's not a lot of points. It becomes a rarity. So that vector xy, that pair of values, is multivariate normally distributed. And it has a mean of 0, 0, being just the mean of x and the mean of y. That will always be the case. Okay, the joint distribution will always have means, the vector mean being the mean of each variable. And now we have what's called a covariance matrix. And those diagonal elements on the covariance matrix are equal to the variances of each individual variable. So you recall that x, which corresponds to the top row here, had a variance of 1, and y had a variance of 2. And then these off-diagonal elements are the covariance between x and y. Some fun facts about the covariance matrix. Again, variances of each variable on the main diagonal, covariances for each pair. I could have more than 2 variables here. Okay, so multivariate doesn't have to mean bivariate. It could mean I have many, many variables. And this matrix will always be symmetric because the covariance of AB is the same as covariance of BA. So again, looking at this now, how can we characterize a point as rare? The answer is different than it was in the univariate normal distribution, because it's not just some constant distance around the mean. It's not just 2 standard deviations away from the mean. Instead, we're going to have what's called a confidence ellipse. Okay, so here in green, I have the 3 sigma ellipse. The 3 sigma ellipse contains about, what, 99.7% of the data. I think it's equivalent to what it is in the univariate. So 3 standard deviations within the mean. Now let's take a look at a bunch of multivariate normal distributions, just to get a sense for how they might look in 2 dimensions. Here, I have a situation where the variance of x is equal to the variance of y, and covariance is 0. When I have a covariance of 0, the data points are completely uncorrelated. And when the variance of the 2 variables is equal, I'm going to get a spherical distribution. Okay, and that has to do with the geometry of the covariance matrix. It turns out to be a circle. If I add some covariance, I take that circle and I stretch it. So here I have a positive covariance of 4. So you can see that as x increases, y tends to increase. If I make it a covariance of -8, the relationship becomes inverted, and as x increases, y tends to decrease. And the stronger the covariance, the tighter that relationship. Now let's go back to a situation where covariance is 0, which means that my data is uncorrelated. And let's consider a situation where I have the variance of x is 3 times that of the variance of y. So what that does is just stretch out the spread along the x direction. And the variance of y is still the same. So let me just give you all of these pictures. on one slide. And again, the purpose here was just to explore that effect of covariance and the relationship between the variance of X and the variance of Y, and getting a sense for what types of different distributions we can make by altering the covariance matrix. When it comes to the actual calculation of covariance, well, the sample covariance is calculated from the data. Again, we have some constant out front. And we are taking the inner product of the centered vector X and the centered vector Y. Again, the centered vector means that we've subtracted the mean from every observation. And so this sum is a sum of the product of corresponding elements. Well, that's an inner product. When covariance is positive, it means that when X is larger than the mean, Y tends to be larger than the mean. Or X smaller than the mean, Y tends to be smaller than the mean. So the relationship is positive. Similarly, when covariance is negative, the relationship is negative. When X is larger, Y tends to be smaller. What we have to keep in mind here, though, is that the units will have a strong effect on this number. So we cannot interpret the magnitude of covariance, only the sign. So what use is it? Well, aside from being a parameter of the normal distribution, it's not much use for interpretation. For interpretation, we reach for correlation, which turns out to be the covariance of the standardized data. Again, the problem with covariance was the scale of the data. What do we do when we have problems with scale? We standardize. So we standardize the data and then compute the covariance. It turns out that is the correlation. So correlation is the inner product between the vectors of standardized data, which of course means that we subtract the mean and divide by the standard deviation. And yes, there's a constant, 1 over n minus 1 out front. And as we should already know, correlation is bounded between -1 and 1, and its magnitude measures the tightness of a relationship. Not the slope, just the strength of that relationship.